Dear students, welcome to the lecture on MET201 Mechanics of Solid, Module 2, Part 1, Stress Strain Diagrams and Constitutive Relations. Myself is Dr. Manoj Tharian, Associate Professor, Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. This lecture will cover the features of stress strain curve for ductile and brittle materials, Poisson's ratio, volumetric strain, the relations between the elastic constant, generalized Hooke's law, and finally we will see what is a plane stress problem and a plane strain problem. A graph showing the variation of stress versus strain for a given material is called the stress strain curve for the given material. The stress strain curve for a given material is an important characteristic of the material. To plot the stress strain curve for a material, we use the universal testing machine shown in this figure. The specimen used in the universal testing machine is shown here. The specimen is clamped between the two jaws at the location shown in the universal testing machine. The cross-sectional area of the cylindrical portion of the test specimen is measured accurately using a micrometer and it is denoted by A0. Two gauge marks are marked on the test specimen at a distance L0 apart. The distance L0 is called the gauge length of the specimen. The test specimen is placed in the testing machine and a centric tensile load P is applied. As the load P is increased, the distance L between the two gauge marks also increases. The distance L is measured accurately using a dial gauge and the specimen is calculated using the relation delta is equal to L minus L0. Delta is calculated at regular intervals and the corresponding load on the test specimen P is also noted. For each pair of readings of P and delta, the nominal stress is computed by dividing P by the original cross-sectional area. That is, sigma is equal to P by A0. The strain epsilon is obtained by dividing the elongation delta by L0. This stress sigma and epsilon calculated are the nominal stress and the nominal strain. Now we plot the curve taking the strain along the x-axis and stress along the y-axis. When the test specimen is stretched beyond a certain limit, a lateral contraction occurs and the area of cross-section of the specimen decreases. The stress computed by dividing the load P by the original cross-sectional area A is termed as the true stress in the specimen. Sigma T is equal to P by A is the true stress. Also, instead of taking strain as delta by L, if we divide each increment of delta L of the distance between the gauge marks by the corresponding value of L, we obtain the elementary strain that is equal to delta L by L. Now adding successive values of delta epsilon, we will get the true strain denoted by epsilon T. Replacing this summation by the integral, we obtain the true strain as epsilon T is equal to integral L0 to L dl by L, that is true strain epsilon T is equal to natural logarithm of L by L0. If we plot the stress strain curve taking the true strain along the x-axis and the true stress sigma T along the y-axis, the stress strain curve obtained is called true stress strain curve. The material that undergoes large permanent deformation before failure are called ductile materials. Structural steel, many class of alloys and other materials belongs to the class of ductile materials. A plot of stress versus strain for a typical ductile material is shown here in this figure. In the portion O to A, the relation between stress and strain is linear. A is called the proportionality limit. The slope of this straight line OA is called the modulus of elasticity for the material. From A to B, the slope of the curve keeps on decreasing. Up to B, the deformation is elastic. That is, when the load is removed, the material regains its original shape. Beyond point B, there will be considerable extension of the specimen which occurs without no noticeable increase in the tensile force. even the load reading will decrease slightly. This phenomenon is called the yielding. Yielding starts at point B. Point C is called the upper yield point and point D is called the lower yield point. The material becomes permanently plastic after point D. The elongation of the ductile material specimen in the perfectly plastic region can be seen typically 10 to 15 times the elongation which occurs in the linear region. After yielding of the material in the region BD, the steel begins to strain harden. During the strain hardening, the material undergoes changes in crystalline structure, resulting in increased resistance to further deformation. Thus, elongation of test specimen requires an increase in tensile load, and therefore the stress strain diagram from point D to point E has a positive slope. The load eventually reaches its maximum value and the corresponding stress at point E is called the ultimate stress. Further stretching of the bar is actually accompanied by a reduction in the load. Here, the diameter of the portion of a specimen begins to decrease because of local instability as shown in this figure. This phenomenon is called necking. The fracture finally occurs at point F. The corresponding stress is called the breaking stress. The rupture occurs along a cone-shaped surface that forms approximately an angle of 45 degrees with the original surface of the specimen. This shows that shear is primarily responsible for the failure of ductile materials. If true stress and strain is used for the plot instead of the nominal stress and strain, the curve obtained is called the true stress strain curve. The true stress strain curve is shown by this dotted line. The decrease in cross-sectional area is too small to have a noticeable effect on the calculation of stress up to point D. Beyond point D, the reduction in cross-sectional area begins to alter the stress strain curve. In the vicinity of the ultimate stress, the reduction in area of the bar becomes clearly visible and pronounced necking of the bar occurs. The stress strain curve obtained is a characteristic of the property of the material and does not depend on the dimensions of the particular specimen. That is, the value of Young's modulus, the value of yield stress, the value of ultimate stress and breaking stress are all material properties and does not depend on the dimensions of the specimen. Materials that fail in tension at relatively low values of strain are called brittle materials. Examples are concrete, cast iron, glass, ceramics, etc. Figure here shows the stress strain curve for a typical brittle material. Brittle materials fails with only little elongation after the proportional limit. The reduction in area is insignificant. The breaking stress is the same as the ultimate stress. Here, in this figure, it shows the tested specimen of a brittle material. We note here the absence of necking of the specimen and observe that rupture occurs along a surface which is perpendicular to the load. Thus, normal stresses are primarily responsible for the failure of a brittle material. Poisson's ratio, denoted by the Greek letter nu, is equal to minus lateral strain divided by the longitudinal strain. First, I will explain what is longitudinal strain and lateral strain with this rectangular block shown in the figure. Consider the rectangular block of length L along the x direction, width B along the y direction and height h along the z direction. The block is subjected to a tensile force capital P along the x direction. The stress along the x direction is given by sigma x is equal to P divided by A, where A is the area, B into H. The stress along the y and z direction are each equal to 0. The strain along the x direction is epsilon x and it is equal to sigma x divided by capital E, where E is the Young's modulus. As can be seen from this figure, when the block is elongated along the x direction due to the force P, there will be a reduction in the cross section. That is, there will be a contraction in the lateral direction. Thus, results in strain along the y and z directions. The strain along the y direction due to the stress along the x direction is called the lateral strain along y direction, and it is denoted by epsilon y dash. Similarly, this lateral strain along the z direction is denoted by epsilon z dash. The dash or prime is used here to denote that this is the lateral strain, that is due to the stress along the longitudinal direction. Now, coming back to the definition for the Poisson's ratio, the negative sign here indicates that when there is an increase in length along the longitudinal direction, there will be a reduction in length along the lateral directions. Also, when there is a reduction in length along the longitudinal direction, there will be an increase in length along the lateral directions. Thus, a tensile stress causes a reduction in cross-section and a compressive stress causes an increase in cross-section. In general, the strain along the lateral direction due to stress along the longitudinal direction is denoted by epsilon dash, and it is equal to minus nu into epsilon. In the case of a homogeneous material which is isotropic, the value of the Poisson's ratio along any direction in the material will be the same. So strain along the y direction and z direction due to the stress along the longitudinal direction will be equal. That is, epsilon y dash is equal to epsilon z dash, and each of these is equal to minus nu into epsilon x. From the figure, we can see that due to the stress along the x direction, the width b gets reduced by an amount delta b. So we get epsilon y dash is equal to delta b by b, which is equal to minus nu into sigma x by e. And also, due to the stress along the x direction, the height h gets reduced by an amount which is equal to delta h. So we get epsilon z dash is equal to delta h by h, which is equal to minus nu into sigma x by e. Now here I am going to explain to you about the volumetric strain. Volumetric strain epsilon v is defined as the ratio of change in volume to the original volume. Consider a cuboid as shown in this figure having sides A, B and C. The cuboid is subjected to stresses sigma 1, sigma 2 and sigma 3 as shown in this figure. The initial volume V of the cuboid is equal to A into B into C. As a result of the stress, the volume will get increased by an amount equal to V plus delta V. Let epsilon 1 be the strain along the direction of A, epsilon 2 be the strain along the direction of B, and epsilon 3 be the strain along the direction of C. So, the new volume of the cuboid V plus delta V is equal to A plus A into epsilon 1 into B plus B epsilon 2 into C plus C epsilon 3. Now, as per the definition of the volumetric strain, it is the ratio of change in volume to the original volume. The change in volume is given by V plus delta V minus V, which is equal to A into B into C into 1 plus epsilon 1 into 1 plus epsilon 2 into 1 plus epsilon 3, which is V plus delta V, minus the initial volume is A into B into C, divided by the original volume A into B into C. So we get epsilon V is equal to 1 plus epsilon 1 into 1 plus epsilon 2 into 1 plus epsilon 3 minus 1. On expanding, we will get this expression. So we know that the strain epsilon 1, epsilon 2 and epsilon 3 are relatively very small. So you can neglect the products epsilon 1 into epsilon 2, epsilon 1 into epsilon 3, epsilon 2 into epsilon 3 and epsilon 1 into epsilon 2 into epsilon 3. So we get the volumetric strain epsilon V is equal to the sum of the linear strains epsilon 1 plus epsilon 2 plus epsilon 3. We have seen the volumetric strain epsilon V is equal to sum of the linear strains, that is epsilon 1 plus epsilon 2 plus epsilon 3. When we have stresses sigma 1, sigma 2, sigma 3 which are mutually perpendicular acting on the cuboid, when we calculate the strain along the direction 1, that is epsilon 1, we should include the effect of lateral strain caused by sigma 2 and sigma 3 along the direction 1, equal to sigma 1 by E from the Hooke's law minus nu into sigma 2 by E by the effect of Poisson's ratio minus nu into sigma 3 by E. The negative sign here is given because the tensile stress sigma 2 and sigma 3 causes a reduction in length and thereby the strain is negative. Similarly, epsilon 2 is equal to sigma 2 by E minus nu into sigma 1 by E minus nu into sigma 3 by E. And epsilon 3 is equal to sigma 3 by E minus nu into sigma 1 by E minus nu into sigma 2 by E. Now, when you substitute these expressions for epsilon 1, epsilon 2 and epsilon 3 in the expression for epsilon V, we will get this expression shown here. On simplifying this expression, we will get epsilon V is equal to sigma 1 plus sigma 2 plus sigma 3 into 1 minus 2 nu divided by E, where E is the Young's modulus. From the expression for the volumetric strain, we will get the expression for the change in volume as delta V is equal to V into sigma 1 plus sigma 2 plus sigma 3 whole into 1 minus 2 nu divided by E. Now, when the force is unidirectional, that is sigma 2 equal to sigma 3 is equal to 0, we will have the volumetric strain epsilon V is equal to delta V by V equal to sigma into 1 minus 2 nu divided by E, or the change in volume delta V is equal to V into epsilon 1 whole into 1 minus 2 nu. Now let me just summarize some of the important formulas we have just now seen, which is important for solving the problems. So when we have a bar or a cuboid which is subjected to forces in three mutually perpendicular directions, the strain along the three mutually perpendicular directions are given by epsilon 1 is equal to sigma 1 by E minus nu into sigma 2 by E minus nu into sigma 3 by E. Similarly, here the expressions for epsilon 2 and epsilon 3 are given. When the state is uniaxial, that is sigma 2 and sigma 3 are 0, we will have epsilon 1 is equal to sigma 1 by E. Similarly, the expressions for epsilon 2 and epsilon 3 are given here. The volumetric strain is given by epsilon V is equal to delta V by V is equal to epsilon 1 plus epsilon 2 plus epsilon 3. That is, volumetric strain is equal to sum of the linear strains. Also, we have volumetric strain epsilon V is equal to sigma 1 plus sigma 2 plus sigma 3 whole into 1 minus 2 nu divided by E. When we have an uniaxial state of stress, that is sigma 2 equal to sigma 3 equal to 0, the volumetric strain is given by epsilon V is equal to sigma into 1 minus 2 nu divided by E, or the change in volume delta V is equal to V into epsilon into 1 minus 2 nu. Based on the concept of volumetric strain which we have seen just now, I'll introduce you to a new elastic constant, namely bulk modulus, which is represented by K. Consider a cube which is subjected to a pressure P from all the sides. The ratio of direct stress to volumetric strain is called bulk modulus. So here in this case, the cube is subjected to a direct stress from all the sides, which is equal to the applied pressure P. So the bulk modulus K is equal to pressure P divided by the volumetric strain. Compressibility is the inverse of bulk modulus. So the elastic constants which we have seen are modulus of elasticity or Young's modulus, represented by E, that is the ratio of normal stress to linear strain, that is equal to sigma by epsilon. The modulus of rigidity or rigidity modulus, it is also called shear modulus, denoted by G, is equal to shear stress by shear strain, that is G is equal to tau by gamma. The elastic constant values for a material mild steel or structural steel are Young's modulus is 210 gigapascal, rigidity modulus is 80 gigapascal, and bulk modulus is 150 gigapascal. So far we have seen 4 different material properties in elasticity, that is the 3 elastic constants, namely Young's modulus, rigidity modulus and bulk modulus, and also we have seen the Poisson's ratio. Out of these 4 material properties, only 2 are independent for a homogeneous and isotropic material. That is, if the value of any 2 material properties are known, the value of other 2 material properties can be analytically found out. Or in other words, there exists a definite relationship among these elastic constants and the Poisson's ratio. So now we will derive the relationship between the elastic constants. Consider the cube which is subjected to pressure P along the three mutually perpendicular directions. So the tube is subjected to a compressive stress of equal magnitude from all the sides. The volumetric strain epsilon V is equal to sigma 1 plus sigma 2 plus sigma 3 into 1 minus 2 nu by E. Here sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to minus P, since the applied pressure is compressive. That is, epsilon V is equal to minus 3P into 1 minus 2 nu by E. The bulk modulus is equal to P by epsilon V, that is equal to minus P divided by minus 3P into 1 minus 2 nu by E, or K is equal to E divided by 3 into 1 minus 2 nu, that is E is equal to 3K into 1 minus 2 nu. So this is the first relationship which connects the Young's modulus and the bulk modulus. We will derive the second relationship between the elastic constants. Consider an element which is subjected to pure shear toe as shown in this figure A. The resultant distortion is shown in figure B, which can be drawn as shown in figure C. The total change in the corner angle is denoted by gamma, which is the shear strain. As angle gamma is very small, the lengths C dash and D dash can be assumed to be arcs. Here, CE is perpendicular to AC dash. Consider the linear strain along AC during the distortion. Linear strain epsilon is equal to the final length of AC, which is equal to AC dash minus the initial length AC divided by AC. We can see AC dash minus AC is equal to EC dash. In this figure, CE is perpendicular to AC dash. So EC dash is equal to CC dash into cos 45 from the triangle CEC dash. Also, from the triangle ABC here, we can write AC is equal to AB by cos 45, which is equal to BC by cos 45, because AB equal to BC. So the linear strain epsilon is equal to gamma into BC into cos square 45 by BC. BC will get cancelled off, and cos square 45 is 1 by 2. So linear strain epsilon along the length AC is equal to gamma by 2. Modulus of rigidity is defined as the ratio of shear stress to shear strain, that is G is equal to tau by gamma. In the previous slide, we have seen that for a stress element which is subject to pure shear, the linear strain epsilon along AC is equal to gamma by 2, or gamma is equal to twice epsilon. Substituting for gamma, we get G is equal to tau divided by 2 into epsilon, or epsilon is equal to tau divided by 2G. Now, as a result of this pure shear state, the normal stress along AC, that is the stress on a plane which makes an angle of 45 degrees with a positive x-axis, can be obtained by using this expression by putting theta is equal to 45 degrees and sigma xx is equal to sigma yy equal to 0 and tau xy is equal to 2. We will see that the normal stress along the direction AC is equal to 2. Also, we can find out the normal stress along direction BD, that is the normal stress on a plane which makes an angle of 135 degrees with a positive x-axis, can also be obtained by this equation, and we will see that the normal stress along DB is equal to minus tau, that is a compressive stress. Now, the linear strain along AC as a result of the stress along AC and the stress perpendicular to it can be obtained using this expression. Epsilon is equal to sigma 1 by E minus nu into sigma 2 by E. Here, the sigma 1 is the stress along the direction where epsilon is measured, that is along AC, that is sigma 1 is equal to tau, and sigma 2 is the stress perpendicular to it, that is sigma 2 is equal to minus 2. Substituting these values, we will get linear strain epsilon is equal to tau by E into 1 plus nu, that is epsilon is equal to tau by E into 1 plus nu is numbered as equation number 3. Equating equations 2 and 3, we get tau by 2G is equal to tau by E into 1 plus nu, that is E is equal to 2G into 1 plus nu. This is the second relationship between the elastic constants, which is numbered as Roman numeral 2. From the first relation, we have E is equal to 3K into 1 minus 2 nu. The second relationship can be written as 2 plus 2 nu is equal to E by G, which is numbered as equation number 4. And from the first relationship, we can write 1 minus 2 nu is equal to E by 3K. Adding equations 4 and 5, we get 3 is equal to 1 by G plus 1 by 3K, which is equal to E divided by 3 kg into 3K plus G, or E is equal to 9 kg divided by 3K plus G. This is the third relationship between the elastic constants, and it is numbered as Roman numeral 3. Thus, the three relationship which connects the four material properties E, G, K and nu are E is equal to 3K into 1 minus 2 nu, E is equal to 2G into 1 plus nu, and E is equal to 9 kg divided by 3K plus G. For an isotropic homogeneous material, using these three relationships, if two material properties are given, the third and the fourth material properties can be found out. The stress at a point is defined by the stress matrix shown in this figure. Corresponding to this stress, the state of strain at the same point be given by this matrix. Now, there exists a definite relationship between the stress components and the strain components. Constitutive relations or generalized Hooke's law relates the state of stress at a point to the state of strain at the same point. It describes the behavior of a material, not the behavior of a body. The 9 rectangular components of stress are related to the 9 rectangular components of strain. That means there will be 81 elastic constants which connects the stress and the strain at a point. Now, due to the equality of cross shear, there are only 6 independent stress components and 6 independent strain components. Thus, the 81 elastic constants will get reduced to 36. In the most generalized case, the mathematical expression which connects the stress to the strain at a point are given here, where A11, A12, etc. are the proportionality constants. Conversely, the expressions which connects the strain at a point to the stress components are shown here. Again, B11, B12 are the proportionality constants or elastic constants. In the previous two slides, we have seen the Hooke's law or the constitutive relation for a generalized material. Now we will see the Hooke's law or the constitutive relation for a homogeneous isotropic material. Before going into that, I will define what is a homogeneous material and what is an isotropic material. In a homogeneous material, the material property is independent of the material position. In the case of an isotropic material, the material property is independent of direction. In an anisotropic material, the material properties are dependent on the direction. Common example we see for anisotropic material are wood and fiber reinforced composite material. The generalized Hooke's law shown in the previous two slides will get reduced as shown in this slide for a homogeneous isotropic material. The expressions for strain components in terms of stress are linear strain epsilon xx is equal to 1 by E into sigma x minus nu into sigma y plus sigma z. Similarly, this is the expression for linear strain epsilon y and the expression for the linear strain epsilon z. Also, the expression for shear strain gamma xy is equal to tau xy by g, where g is the modulus of rigidity or the shear modulus. Gamma xz is equal to tau xz by g and gamma yz is equal to tau yz by g. The stress components can be expressed in terms of the strain components as normal stress sigma xx is equal to E divided by 1 plus nu into epsilon x plus E into nu divided by 1 plus nu into 1 minus 2 nu into epsilon x plus epsilon y plus epsilon z. Here is the expression for the normal stress sigma y and the expression for the normal stress sigma z. Also, the shear stress tau xy is equal to g into gamma xy, tau xz is equal to g into gamma xz, and tau yz is equal to g into gamma yz. The expressions for strain components in terms of the stress components for a homogeneous isotropic material shown in the previous slide can be written in the matrix form as given here. Also, the expressions for the stress components in terms of the strain components for a homogeneous isotropic material can be written in the matrix form as given here. Here, this is the stress matrix. This square matrix shown here is the constitutive matrix for a homogeneous isotropic material, and this is the strain matrix. The application of Hooke's law is explained using a numerical example given here. In the question, we are given the strain matrix at a point. We are asked to determine the principal stress and the corresponding principal plane. Take the modulus of elasticity E is equal to 2.07 into 10 raised to 5 megapascal, and the modulus of rigidity G is equal to 0.8 into 10 raised to 5 megapascal. Using the relation connecting the Young's modulus, Poisson's ratio, and the modulus of rigidity, we can find out the Poisson's ratio nu. We will obtain the Poisson's ratio nu is equal to 0.294. Then, using the stress-strain relationship for a homogeneous isotropic material, which is given here, we can find out the corresponding stress matrix at the point P. Using the above equations, we get the stress matrix at the given point as shown here. We will use this stress matrix and the usual procedure for finding the principal stress to find out the principal stresses at point P. The principal stresses obtained are sigma 1 is equal to 30.66 megapascal, sigma 2 is equal to minus 326.15 megapascal, and sigma 3 is equal to minus 709.39 megapascal. The direction cosines of the corresponding principal planes are also given here. The previous problem can be solved also using the following method. First, we find out the Poisson's ratio using the relationship E is equal to 2G into 1 plus mu. Once we get the Poisson's ratio, for the given strain matrix, we will find out the principal strains epsilon 1, epsilon 2, and epsilon 3 using the usual procedure for finding the principal strain. Also, we find the direction cosines of the principal planes. Now, the strain matrix at the given point with respect to the principal coordinates 1, 2, and 3 can be written as shown in this matrix. Once we have obtained the principal strains, we can write the strain matrix with respect to the principal coordinates 1, 2, and 3. So here is the strain matrix with respect to the coordinates 1, 2, 3. Note that here the shear strains are 0 because the principal plane is a plane where the shear strain is 0. Now we can use this strain matrix in the stress-strain relationship to find out the corresponding stresses. The corresponding stresses are the principal stresses. So when we use this stress-strain relationship, instead of epsilon x, we will substitute epsilon 1. Instead of epsilon y, we will substitute epsilon 2. And instead of epsilon z, we will substitute epsilon 3. Also, the shear strains gamma xy is equal to 0, gamma xz is equal to 0, and gamma yz also equal to 0. Now, using the stress-strain relationship, the principal stresses we obtain are given here. Sigma 1 is equal to 30.66 megapascal, sigma 2 is equal to minus 326.15 megapascal, and sigma 3 is equal to minus 709.39 megapascal. The corresponding principal planes direction cosines are the same as we have obtained for the principal strains. So here we see that we obtain the same answers as we have obtained in the previous method. Now we will see what is a plane stress problem. So here the matrix shows the generalized state of stress at a point. Now in certain specific cases, tau xz is equal to tau yz is equal to sigma z equal to 0. In this case, our generalized state of stress will get reduced to the form as shown here. Here we see that there are only three independent stress components, namely sigma x and sigma y, the normal stresses, and the only shear stress present is tau xy. This stress state is known as plane stress state. Examples for plane stress problems are a thin plate subjected to in-plane forces. Second example is laterally loaded beams. And the third example is stresses occurring in a rotating disk. So these are the classical examples for plane stress problems. Now in the case of plane stress problem, the Hooke's law will get reduced to the form epsilon xx is equal to 1 by E into sigma xx minus nu into sigma yy. Epsilon yy is equal to 1 by E into sigma yy minus nu into sigma x. And epsilon z is equal to minus nu by E into sigma x plus sigma y. And the shear stress gamma xy is equal to tau xy by g. Similarly, for the plane strain problems, in the generalized state of strain, epsilon zz is equal to gamma xz equal to gamma yz equal to 0, and the state of strain will get reduced to the matrix as shown here. Here there are only three independent strain components, namely epsilon xx and epsilon yy, which are the linear strain components, and the only shear strain component is gamma xy. So this is a plane strain problem. The examples for plane strain problems are retaining wall with a lateral load. Here dams are a classical example for plane strain problems. Another example is a long cylinder subjected to internal and external pressure. The Hooke's law for the plane strain problem will get reduced to the form epsilon xx is equal to 1 by 2g into sigma xx minus nu into sigma xx plus sigma yy. Epsilon yy is equal to 1 by 2g into sigma yy minus nu into sigma xx plus sigma yy, and gamma xy is equal to 1 by g into tau xy. The expression for sigma zz is equal to nu into sigma xx plus sigma yy. Before I conclude, let me just summarize what we have learned in this lecture. Initially, we have seen the stress strain curve for a ductile and brittle materials. I have introduced you to the concept of Poisson's ratio, volumetric strain. Then we have established the relationship between the various elastic constants, and also we have seen the generalized Hooke's law and the Hooke's law for plane stress and plane strain problems. So thank you all for your patient listening.